So, welcome to lecture 8. And in the lecture 7, we started talking about set theory and fuzzy set theory. And the reason for doing this was we wanted to see what would happen if we impose fuzzy logic on the Euclidean space. Then what would happen to geometry? How does its structure look like? And I wanted to show this, and for this, I think it was very important that I should that I tell you about set theory a little bit and fuzzy set theory, because without having those ideas, it would be very complicated to understand what you are going to do here. And last time we gave some very little surface kind of introduction to set theory and little fuzzy set theory. In this video we are going to do it. I'm going to introduce you the idea of fuzzy set, and from there we will start to see, and then the nature of geometry that we will get after imposing this structure fuzzy logic on top of it. So I think maybe we should start doing on this paper. And so yeah, so last time we said we have the symbol called belongs to. This is the symbol called belongs to, and we also defined a membership function. Like if a set F is given and it has elements A, B, C, dot dot dot, so on. Let's say A, B, C, D, finite set. It is finite set because it has finite number of elements. So we define a function, and the notation is mu. And it acts on the function set F, and let's say there is element X. So what it says that the function becomes 1 if this X belongs to this F. So we can write 1 if X belongs to F, means X is in the set F, and 0 if X does not belongs to F, if X does not belongs to F. Now we can evaluate this function for each of these values. For example, mu F of, let's say I'm gonna pick an element from this, let's say C. So in the place of X we can put C. So this value C, what is the answer for this if you evaluate this? Because you can see that this C, like it would be 1 if C belongs to F, 0 if C does not belongs to F. So what would be the answer for this? We know C is in the set F, so C belongs to F, and since C belongs to F, the answer is 1. So 1. So we got mu F of C is equal to 1. How about mu F of apple? Well, it is 1 if apple belongs to this set, 0 if apple does not belongs to F. Now see here, does apple belongs to F in the set? No, it means apple does not belongs to F, so answer is 0. So it would be 0. So mu apple, the membership value of apple belonging to this set F is 0, right? So this is for the crisp set. It is called classical set theory, right? And classical set theory, so this membership, what this membership is doing is like it's a function that take a set from X. It's defined on a set A, which takes a element of the set A, and then it transitions this element to a set of 0, 1. That's the value. It's a function from a element to the element of the set to the this discrete value, you know. Now this idea is extended to this concept of fuzziness, and this is how that's what we are going to see. So the idea of fuzziness is like the membership would be the set would look like this, some kind of we can say, let's say there is a set A, then the fuzzy set has the notation quite bizarre like this. Member, it's a set, and this is a set, and on the set we are going to define this fuzzy set, and this is the membership value of the x that belongs to the set A, and such that this x belongs to this x. And the membership, this would look like something like this. So this function membership, it look like take this, but 0 to 1, this is closed interval. This is closed interval. Closed interval means here you have a real line. Let's say 0, here is 1, here is 2, here is 3, here is -1, -2, and so on. This closed interval means all the number between 0 and 1. So we have to put circle here and paint it, and then we have to do this, and these all values between 0 and 1 it can take. Also 0 and 1 is in this set. So this is, if I expand it, it simply means mu of x is equal to, it is 0 if x does not belongs to A, it is 1 if x belongs to A. So this is no membership, no belonging. This is full membership. It means it is completely belong to the set, and this value is in between 0 and 1 if partial membership. Partial. So this is how we define this function. 0, 1 means all the values between 0 and 1 except 0 and 1, because we have already taken here 0 and 1. This is open interval. It looks like this: 0, 1, 2, and so on. Here is -1, -2, so on. So in between 0 and 1, but we are not going to paint this one. This open circle means we are not going to take 0 and 1 into this, only the in between this value. But here we have to take 0 and 1 too, because this is closed interval. This symbol closed interval, right? So this is how fuzzy set is defined, right? Now we can go and ask the geometrical question where we impose fuzzy set on the Euclidean space and see what happens. So the fuzzy geometry, this is notation GF, fuzzy geometry is, we take Euclidean space, regular Euclidean space, the normal, and we impose fuzzy logic here, and that is what our fuzzy geometry is. Whereas Euclidean geometry is like the same Euclidean space but classical logic imposed on it, right? Now in this we have same flat space, Euclidean, and fuzzy logic is imposed upon it. We have imposed fuzzy logic upon it. Then we ask, what is a line then? See, a line, I am going to talk about little coordinate geometry. Coordinate geometry is algebra imposed on geometry, right? So now a line has representation with an equation. In Euclidean geometry we have this is a line, but René Descartes, after having the idea of plane and giving notation plane with some real lines, and after that he came to the conclusion that a line can be represented using algebraic equation, a linear equation, which is like ax plus by plus c equal to 0. This is a line. Now this line, let's say we have a point pxy, and if this pxy belongs to this line L, let's say this is line L. So if pxy belongs to this line L, then it means if we substitute value of x and y in this line, we get 0 answer. And if we do not get 0 answer, it means this point does not belongs to this line. For example, let's we have another point px1 y1, and let's say we substitute x1 y1 in this line, so we get ax1 plus by1 plus c. Suppose this is not 0, then what does it mean? It means this point does not belongs to this line. Here we substituted x and y into this equation and we got 0. It means this point belongs to this line. So this is either 0 or not 0. Either belongs to this point or it does not belongs to this point. This is classical thinking. Classical thinking. But we know fuzzy set says if there is a point, mu point, then its value can take the values this from all these closed intervals 0, 1 and in between all those numbers, right? So now line, what is line then? So now line is no longer something, a point either belongs to or does not belongs to, right? Because here what was the idea? Given a line, let's say a line is given ax plus by plus c equal to 0, then what do we say? If there is a point x1 comma y1 and another point, let's say this is p1 point, this is p2 point, its coordinate are x2 y2, then what do we say? If we substitute this value here, let's say we are going to substitute, then ax1 plus by1 plus c, suppose this entails 0, then it means what? This p1 point 1 1, this belongs to this line L, because after substituting this value into this line we got 0. But for this, suppose we substituted x2 y2 plus c and it is not 0, then what does it mean? It means this point x2 comma y2, it does not belongs to this line L, right? So it is either belongs to or does not belong to. That is how we define a line. But here we know this, that classical, this fuzzy set says x, y can take all the values between 0 and 1. So now line is no longer something a point either belongs to or does not belongs to. Instead, we can say a line becomes, and this is very important, instead a line becomes a membership field over a plane. Now this is very important. We are going to dissect what does it mean. We said line is no longer something a point either belongs to or does not belongs to, because we are not talking about crisp set, a classical set theory. We are now extending this to fuzzy. It means the point can belong 0.5%, 5% or 10% or 30%, right? Here it was a point can either belongs to 0% or it belongs to 100%, either yes or no. But here a point can belong maybe 1%, maybe 10%, maybe 30%. So now what is a line? Because a line has points. We can impose points on it. So now suppose this is the point. So how much this point belongs to this line L? Classical set theory says it is 100%. And suppose here is another point. How much this line belongs to this? 0%. But now in fuzzy logic we cannot say that. So now how does our line look like? So instead a line becomes a membership field over a plane. What does it mean? So we define line like this. A line is what? So line is, we can take it as a set. Line is a set of points, you can say, but this is a very not a good way to think, but I will make clear why we say this. But suppose for now, what does it take? It takes r square to 0 and 1. This is how we define a line. So this fuzzy line is a, we can say this fuzzy line. So this, we get a fuzzy line which is a geometric probability like, not probability, probability like field over r square. What does it mean? It means a line is no longer a one-dimensional object. One-dimensional object means an object which has only length. So in Euclidean geometry, a line has only length, so it is one dimension. But here, a line is now no longer a one-dimensional object. In a strict sense, we can say. Right? What is it now? Then it is now a different kind of object. We can imagine it as a ridge of maximal membership. A ridge of maximal membership in plane. Right? But this is after we imposed a optimization structure. Optimization structure in this. It means, what I'm trying to say is, now a line, how does your line look like? Now in classical geometry, our line was like this, one dimension length. Now in fuzzy geometry, your line may look something like a blur two-dimensional region, like this kind of things. You see? Now this point is like a laser light, a very blurry, a cloudy kind of things. So it's a very different kind of region. We can make optimization that this is the maximal region where the most of the points belongs to, but that is after optimization that we choose, impose upon it. Otherwise it's just it's like a two-dimensional blurry line, but it gets here will be more dark region, a dark region, and it gets blurry and blurry when you go away from it. Blurry and blurry. It's like this, right? So it's a field of belonging over a set. A line is field of belonging over a set. Whereas in Euclidean geometry, a line was just a set. Line is a set in Euclidean geometry. But here a line is a field. It's like a field, you can see here. It's a very a field of belonging over the set. So Euclidean geometry was geometry of set, and we move from geometry of set to geometry of functions in fuzzy geometry, right? So now this, if you see here, this is a field. It's a 2D region with a gradient structure. Gradient means how much point belongs to something, and you can see here gradient. When we go away from the sharper region, you get more blurry region, faded region, faded. So it's a gradient, increasing, decreasing, right? So now what happens to the postulate like this? Given a two line on the plane L and M, either they intersect or they don't. So what happens to this in fuzzy set? Well, in fuzzy set, a line can be blurry like this, right? So this, and suppose there is another line given here, this one. So it also has this field going over. Now see, this is L1, this is L2. We can say L and M, that doesn't matter. Name is not important. Now see, this line, the field of this line and the field of this line are getting overlap here, right? So now what is intersection of a line? So what is intersection of the line? That is the question we are trying to answer. Now two lines intersect, L1 intersect L2. This is a symbol for intersect, meeting. It means line 1 and line 2 meet. Now if this is equal to phi means 0. If they do not intersect, it means they are parallel. But if L1 intersect L2 is not equal to phi. It means they are meeting. It means they intersect. So this is binary, either meet or they do not meet. But here, the fields are overlapping. So we need a different kind of functions. We need to define intersection. This is meeting. Intersection of two lines L1, L2 is not 0 and not 1. 0 means parallel. L1, L2 has no intersection, no common element. It means 0. They are not intersecting, so they are parallel. L1, L2 has intersection 1. It means they are meeting, so they are meeting. So either 1 or 0. But here it is not 1 and 0. Here we have to define intersection of two lines L1, L2 belongs to this 0, 1 close interval. Now we can only say L1 and L2 intersect 30% or maybe 40% or maybe 0%. If they are 0%, it means they are parallel. 100%, it means they are completely full intersection. So it's a different kind of thing going on now, right? So now the very idea of parallelism, what is parallelism, is completely changed now. Now we also talked about given a line and a point, a line L and a point P, there is exactly one line passing through this point, that is parallel to this line. But this is not correct now, because now infinite line can be passing through this point and they all will be parallel to this, because it is a field now. So infinite line passes. See, the geometry has completely changed. This is what we are trying to say. The fuzzy logic imposed upon Euclidean space has a completely different kind of geometry, has completely different notion of what a line is, what parallelism is, what does intersection means, right? So this has completely changed. And this shows that Euclidean geometry assumes classical logic. And that is a very different kind of geometry. The classical logic is embedded into Euclidean geometry by Euclid. The moment we change this classical logic to fuzzy logic, we are into a very different kind of world here now, right? So now, in the next lecture, we will try to clear one very important thing, and that thing will be the idea of point, line, plane, and three-dimensional space. And we'll try to solve a paradox which was in the last lecture, not last lecture, maybe second or third lecture. We talked about how come point has no size, but after collecting all those points together, it makes a line and then it becomes a size. Well, if everything is point, then summing point plus infinite point, if you add, and all had zero size, it should be zero. So the length should not be any, so there cannot be any length. It cannot produce a length. It should be zero. And that was the paradox. So how does it happen? So this is what we are going to try to see in the next video, right? Okay.